Another problem, these just go on and on in this section, don't they? They do, because this is a really important section. You fully have to have a grasp on all of these types of problems. So that's why I want to make sure I go through them with you, to make sure you're completely prepared, and you can pass that mastery check, the exit ticket, without issues. So let's get to it. What we're looking at is a modified Atwood machine. We have a 12 kilogram mass on a surface. That's why it's modified. Normal Atwood's machines have just 2 masses or 3 masses and 1 pulley. This, we have 2 masses, pulley, and a table. So that table is going to introduce friction, which tells us there's a kinetic friction of 0.5. Draw a free body diagram for the time each object is released. So let's go ahead and get to it. So we have this 12 kilogram object, which is going to have the easy force, right? mg. Going up, we have Fn. We've got tension to the right. What did I make that? 2 boxes. Then I'll make friction 1 box. Because I made my tension force to the right 2 boxes, I'm going to make my tension force going up 2 boxes as well. And then my weight, 3 boxes. Because I know once this is released, this object is going to go down, this object is going to go right. Okay, so without reading any more of the question, I know my next step after drawing a free body diagram would be to create my Newton's second law equations. Stuff that makes it go minus the stuff that holds it back equals mass times acceleration. So let's go on to these equations. First we'll do the 12 kilogram. The stuff that makes it go is going to be that tension force. The stuff holding it back is going to be the frictional force equals, I'm going to call that m1 times acceleration. Next one, we have m2g minus ft equals m2a. And then for the entire system, the whole thing, this is going to go down and this is going to go to the right. So the stuff making it go is going to be m2g minus the stuff holding it back, which is this frictional force acting on the heavy mass, equals the combined masses, 1 plus 2, times the system's acceleration. Here you can substitute in your numbers, if you like. Let's go ahead and do that. m2g, so that's going to be 8 times 10 is going to be 80. Now this is free response, so yes, you could and should use 9.8. But if you use 10, that's okay, as long as you put somewhere g equals 10 meters per second squared. So we're covered. Frictional force. We know the frictional force is mu, which was given to us as 0.5, times the normal force, which is equal and opposite to this. So this was 120. So half of 120 equals combined mass 20 times A. So we have 80 minus 60 is 20. Divide 20 from each side to get A all by itself. And we have A equals 1 meter per second squared. Now, I'm going to take that A equals 1 meter per second squared. That's kind of a funny looking A. Clean, 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 clean. There. Yeah, that looks great. Now, I can take this 1 meter per second squared, and I'm going to plug it into this equation. When I do that, I have Ft minus Ff. Remember, I'm solving for Ft right here. Mass 1 was the 12 times 1, so that's going to equal 12. My frictional force, I said earlier, was 60, so I'm going to add 60 to each side. And I get my tension to be 72 newtons. So there you go. I have all of my steps, I have all of my work. This should get me full credit, as long as I didn't mess something up. Which I didn't, relax. Next one. 3 kilogram cart having a frictionless bearings is set on a table. frictionless. That's probably going to be important. In the three cases, the card is attached to a hanging mass by a string that passes over an ideal pulley. What's an ideal pulley? Massless, frictionless. The hanging mass is different in each case. The acceleration in case... Alright, so student 1 says the acceleration in case 1 is 0. Case 1. Because the cart on the table is greater than the hanging mass. This means the hanging mass does not have enough force to cause the cart to move. What do you think? I think this can be solved with a free body diagram. We have tension pulling this way and we have weight pulling down, right? We do not have any friction pulling back. So as this goes down, this is going to slide to the right. Frictionless bearings. So that tells me the bearings are frictionless, so they're allowed to rotate freely, but there is a static friction between the table and the wheels because it's allowing it to roll forward. Okay, so sorry, student 1, that is incorrect. And I would just say no. Incorrect because there is a forward force M1 times G, or you can call it FW, maybe more appropriate for this, FW, without friction holding it back. I don't know what this is like for you guys watching me write this, but for me it's a bit of a nightmare. Without friction holding cart 2 back. So it will accelerate. Accelerate because, the important part, the net force is not 0 on cart 2. So without there being a net force, there must be an acceleration. I'm erasing that because I'm probably going to need it. What's next? Student 2, the acceleration in case 3 is greater than 9.8 meters per second squared because the force is 50 newtons and the mass is 3 kilograms. Dividing force by mass gives an acceleration greater than g. That's not how physics works. Because if we look at this as a total system, the total mass, remember, is 8, 5 plus 3. You go back to the last problem where we did that system. Then we did the stuff that makes it go is mg minus the stuff that holds it back. Well, in that last problem there was friction here, but in this case it's not friction going backwards. So it's going to go down with an acceleration of, so the stuff that makes it go minus nothing.